P and Q, of masses 0.4 kilograms and m kilograms respectively, are joined by a light and extensible string, which passes over a smooth pulley. The particles are released from rest at the same height above a horizontal surface. The string is taut, and portions of the string not in contact with the pulley are vertical. Q begins to descend with an acceleration of 2.45 meters per second and reaches the surface 0.3 seconds after being released. Subsequently, Q remains at rest and P never reaches the pulley. Calculate the tension in the string while Q is in motion. Calculate the momentum lost by Q when it reaches the surface. Calculate the greatest height of P above the surface. Let's have a little look at this then. Here's the question in summary form. I've put one of the tensions in already. I'll put another tension in here as well. And this 0.4 kilogram must have weight 0.4 g, mustn't it? This weight here, because it's mass m, will be mg. So that's the acceleration. They're released from rest at the same height. So the height here we can label as h. Right, so let's have a look at this then. Calculate the tension in the string. So if we look at P, resolving forces upwards then, applying F equals ma, gives, so the force upwards then, tension minus 0.4 g, is equal to the mass, 0.4, times the acceleration. Well, the acceleration upwards here will be the same as the acceleration down on the other side, which is 2.45. So put that in. So that tells us then tension is equal to, now let's just move this over here and add them together. So let's do that then. So, move the 0.4 g over, plus this amount here, which I'll tap in the calculator, 0.4 times 2.45, 0.98. So that tells us what the tension is then. It's this 0.98 plus 0.4 g times 9.8, 4.9. Newtons is the tension in the string. Calculate the momentum lost by Q. Well, we need the mass, don't we? So let's apply Newton's law at Q then. At Q, let's apply it downwards because it's moving down. F equals ma then. Gives. So it would be mg minus the tension in the rope, minus T, is equal to mass m times acceleration 2.45 times 2.45. So move this over, m g minus the 2.45, isn't it? Is equal to the tension, which is equal to 4.9. So that tells us what the mass is. 4.9 divided by g minus 2.45. So we got the 4.9 in the calculator, divided by bracket 9.8 minus 2.45, close bracket, 2/3 of a kilogram. Okay, there's our mass. So we've got the mass of the object then, 2/3. We know its acceleration, we know its time, so we can work out the velocity, can't we? So here, u is equal to 0, it's released from rest. A is equal to 2.45. T is equal to 0.3, wasn't it, seconds? Mentioned in the question here, when it hits. So v equals u plus at gives, so the final velocity then is equal to 0 plus at 2.45 times 0.3. Put it in the calculator. 0.735 meters per second. So there's the velocity of the Q on impact. So momentum lost. It doesn't have any momentum after because it just hits the ground and stays there. Must be m times v. 2/3 is the mass times 0.735. So times this by 2/3 then. 49 over 100. 0.49. Momentum is m kilograms, v meters per second. So there's the momentum lost then. Okay, so what have we got then? We've got that. Now, what's this height? Now P, we need to calculate the greatest height of P. Well, this height here is how much P will move up to start with before this hits. So we need to work out that. So I've called it H. So this is part 3 now. The previous part was part 2, wasn't it? And the first beginning was part 1. So 3, if we use S equals ut plus half at squared, we know the time, we know the acceleration, and we know the initial velocity. So S will be the height at Q falls or P rises. U is 0, half times 2.45 times the t squared. So we need to type that in the calculator. 0.5 times 2.45 times 0.3 squared. 441 over 4,000. 441 over 4000 meters. And we can get the decimal, write down the decimal if we wish. 0.11025. Meters. Okay, there's the height. So P, if we look back at our diagram then, P will ascend that amount as well as that Q falls. So let's draw a fresh picture. So we've got P here. This distance here is 0.11025, and this is P, and it goes up to here, and this is another, because Q falls 0.11025 as well, so P will rise that much again, and then Q hits the ground, so it just rises due to gravity. The velocity here going up, the initial velocity will be the final velocity down the bottom, which we worked out to be 0.735. The acceleration is gravity. The speed here, which we can label as v now, is 0. We need the distance, which we'll call s. So here, v squared, which is not, let's invoke that formula then. V squared equals u squared plus 2as gives, so the final speed at the top of flight will be 0. The initial speed will be 0.735 squared plus 2a. Acceleration is minus g, so it's minus 2gs. So that tells us what s is then. The 2g can come here, and we can leave, so I've moved this over there. 0.735 squared. And that tells us that s is equal to 0.735 squared. And move the 2g down. So S equals 0.735 squared divided by bracket 2 times G, 9.8. 441 over 16,000. So I'm going to leave it as a fraction. 441 over 16,000 because it's easier to handle. So answer then, total. So what did we want in part 3? Greatest height of P above the ground. Greatest height. So answer then will equal 2 times this and this, 0.11025, plus this height that it raises up, 441 over 16,000. So we got that in the calculator here. So add on 2 times 0.11025 equals 0.248. And that's the 3 significant figures.